My name is Noah Rodriguez, and my team and I will be presenting the research we did, in which we built what we call the Aspectum rover. Aspectum is Latin for sight, which ties into the goal of this rover. We wanted to design a device that could see other parts of planetary bodies with a precision that is impossible from here on Earth. The way we did this was the rover uses a GPS sensor to constantly track its coordinates as it traces over a particular patch of land. Then we can take those coordinates and make a topographical map of what the ground looks like. And then we can use the rover also has a sampling device in which we can take a sample of the ground. And so with the sample and with the topographical map, we have an idea of what the ground looks like and what it feels like. The application for this rover is we wanted to design something that would act as a kind of a scouting device for the human landing systems that NASA plans to use as part of its upcoming Artemis missions. And so it would scout out the plot of land that the human landing systems plan to land on so that landings can be performed with more safety and precision. So I'm going to hand this over to Caesar, my partner Caesar, and he's going to explain how we got our rover rolling.
Hello, my name is Cesar Winrostro, and as Noah was just saying, I am now going to explain to you how this rover operates. First off, we were using 4 low-powered DC motors that each come equipped with a driver shaft that allow us to attach these Omni wheels shown here. The Omni wheels were designed in a way to provide for maximum traction and enhanced maneuverability while navigating over difficult terrain. To steer the rover, we are using an Arduino Uno that is attached to this driver shield shown here. This setup allows the rover to move forward, backward, to the left, and to the right. To power this, we are using a 12-volt LiPo battery that can give us a long battery life while still providing all the power that we need. I'm now going to hand you back to Noah, who is going to talk about the wireless capabilities of this rover.
Thanks, Caesar. So to control the rover wirelessly, we use the HC06 Bluetooth module, which acts as a wireless serial port between my computer and the Arduino. This way, the Arduino could receive inputs as though it were still plugged in. And so we programmed the Arduino to receive character commands so that we could use the W, A, S, and D keys as arrow keys for the rover, with W being forward, S being backward, and so on. Here's a little video of the rover in action. And next I'm going to ask my partner Michael to explain the data collection and graphing system.
Thank you, Noah. Hi, my name is Michael, and I'll be describing the data collection and graphing process. To start, our GPS data comes from the GPS breakout sensor shown here. The sensor provides longitude, latitude, and elevation, which serve as our X and Y and Z coordinates for our topographical plot. The GPS sensor is then interfaced by an Arduino Mega as shown here. We decided to utilize a Mega due to its extensive pinout selection, allowing us to add more sensors if needed in the future. To transmit data from the GPS to the Mega, from the Mega to my computer, we utilized the NRF2401 radio transceiver module. We chose radio over Bluetooth due to its extended range, allowing us to better plot data. The radio module on the Mega, which is placed on the rover, that sends data to the corresponding radio module on the Arduino Nano, which is plugged into my computer. After this data is received, it is then processed serially through Node-RED, an event managing software that allows us to then take this information and store it into the database, which we're managing through phpMyAdmin. Here we have created a 3D topographical mesh plot, and here's a video showcasing how we created this plot. As you can see in this video, it is not complete as we only graphed a few square feet, and that was our topographical mesh. Now I will pass it over to my teammate Jacinto, who will explain how he designed the sampling device for our rover.
Thanks, Michael. Hello, I am Jacinto Mangiari. Now I will explain how our sample collection system works. The design is inspired by an excavator, which when drilling into the ground traps the sample inside a pipe with a drill-shaped surface. The entire model was designed in SolidWorks, Although our early prototypes considered using a robotic arm to collect samples, we ultimately chose a drill-based mechanism due to its simplicity and effectiveness for sample collection. Here we can see all the components of the sample collector: the mount, the base, the connection between the linear actuator and the DC motor, and the pipe. And here we can see the fully assembled system. This video shows us an explode view animation that help us better understand the arrangement of the internal components. And for 3D printing we use the Anycubic Cobra Mats printer, as for material we use the black and white PLA filament. In these images we can observe some of the printed parts, as well as the sample collector before it was mounted onto a rover. And here we can see the separate. How it's assembled. The system consists of a linear actuator which is secured to the main mounting frame using a screw. On the moving end of the actuator, a DC motor is attached via a 3D printer connector that links both components. This connection is also reinforced with a screw to ensure stability during operation. Finally, the sample pipe is directly attached to the rotating shaft of the DC motor. To achieve this connection, I use the technique called thermal interference fit. I hit the metal shaft of the motor and quickly insert it into the plastic pipe so that upon cooling it would bond tightly. How it works. The linear actuator pushes the entire assembly, the motor and the pipe, downward with significant force, allowing the pipe to penetrate the ground. Then the DC motor begins to rotate, spinning the pipe, which has a drill-like shape to ease its entry into the soil. Thanks to this combination of downward force and rotation, the samples become trapped inside the pipe, which has an internal cavity specifically designed to collect them. Additionally, we use an Arduino to control the system, a motor driver to power the actuator and motor, a Bluetooth module for wireless control, and a 9-volt depot battery as the power source.
That concludes our presentation. And so on behalf of the Aspectum team, I would like to thank you all for watching, and I would like to thank NASA for this research opportunity. Thank you.